Good evening, folks. I hope you had great conversations with each other just now, and if not, I hope you at least enjoyed the pizza and the drinks. Uh, Today, I'd like to tell a story about how to build AI applications, but in a way where like AI and data work together. Because I know we've all heard data and AI nonstop, but oftentimes it's kind of like the data side is completely disconnected from the AI side. And I want to show you like a dream, right? A dream where both are working seamlessly together. So to start off, I thought I'd give a little bit of context of where I'm coming from. And when I was making these slides, I used our standard company's About Me template. And here I put like where I worked before. I worked at Databricks and Photon. I work at Eventual. And right, so it does actually give a good context of why I think what we're building is pretty exciting. And so I messed around with the slides a bit. Mostly I tried to like make it more descriptive in the sense that like at Databricks I just made stuff fast, and at Eventual I also made stuff fast. Um, but then I thought to really give you a context of why I think this application we're going to build is interesting, I'm going to start from the start, like the whole domino thing from when I was 13 here, a happy young lad, all the way to where I am today. And we're going to like see some major events along the way. So first, it's a little small, but first in 2010, I see my brother generating prime numbers on the Windows console. I thought it was really cool. I saw it. I wanted to be a hacker. Great. 2016, AlphaGo beats Lee Sedol, and I thought, wow, this is really cool. Now I really want to do machine learning instead of being a hacker. But then in 2020, something eventful happened. I tried computer vision for the first time and decided I never wanted to do machine learning in my life because it really sucked. I was like, I spent most of my time doing like pre-processing the images, normalizing them, and then trying to make TensorFlow work. It kind of sucked. Um, I thought, okay, I'm not going to do machine learning. I'm going to do data science because everyone's talking about it now in 2020. I did a data science internship and quickly decided I'm never going to do data science in my life again, too, because the two sucked. I thought, okay, great. Machine learning is out, data science is out for me. I'm going to do data engineering. And so I TA a course in data engineering. And back in that day, we were like teaching Apache Spark and writing like RDDs and everything. And it really sucked. And I decided I never wanted to do data engineering again. And I was like pretty distraught because you notice all this is happening in 2020. Like in the same year, I decided that all the things I wanted to do with data, I wasn't going to do. So I can only aptly describe it as like my sad cowboy years. I was a bit lost. I didn't know what to do with computer science at this point. And so I always thought, if you're lost, you should think back to your elders and be inspired by the greats. And so I thought of my hero, Batman. And I decided that I would be the hero that people deserved and not the hero we needed. And I would go deep into the data tools themselves and make the data tool I never had growing up. And so I went very hard into database systems. I started off by doing what I call irreparable damage to how database systems are taught at my university. They still have not recovered from what I did that year in rewriting the course. In 2022, I joined Databricks, where I made it my life mission to make business intelligence really fast. And then in 2024, I finally went on to my real dream of making AI and data tools that spark joy and didn't suck. And so that's where Daft comes in, right? And remember, what we're building here is not just a data tool to do data science and machine learning. We're building a tool so that no one else has to go through this journey of wanting to do ML, hitting a bunch of roadblocks and saying, I never want to do ML again. We want it to spark joy. So how are we going to do that with Daft? Let's break it down first. What is Daft? Daft is a Rust-based data engine that works with multimodal data, like images, videos, audio, embedding, so on and so forth. It scales seamlessly from local development all the way to distributed compute. And we're going to take all these buzzwords that every data system out there likes to throw out and see what the ideal story is, how we're going to have a happy customer. And so the happy customer today is going to be me. And as someone doing data and AI, I want to work with tools I'm familiar with or languages I'm familiar with. In this case, it's going to be Python and SQL. Python, because if we're working with ML libraries, we really want to stick with the Python ecosystem. I don't want to understand Java. I don't want to install jars. I don't want to manage Hadoop versions. SQL, because I worked for 2 years at Databricks and I only know how to do SQL for data engineering. Nowadays, if you're doing like AI and ML, you're going to do it in the context of a big company. You're going to have production-based data. You're going to have teams of data engineers getting the data ready for you. Because of this, any data tool out there needs to natively understand data catalogs and work seamlessly with it. If you're handling a bunch of data, you probably have some sort of like normalization over the data. You're going to join different kinds of data together. You need to work with large-scale joins and large-scale data. And now when I hear large joins and large data, I hear the flap of money flying away, right? And so we need our tools to be performant. These days, it's not sufficient to be a data engine that just works on numbers and short strings. We need to work on multimodal data, images, videos, so on and so forth. We need to work on multimodal data at scale. And this is kind of where like we think the partnership of any skill comes in that, if you're scaling up, this is where we need distributed compute. And lastly, after you have all your data ready for you to use, you want to do AI on top of it, whether it's making calls to LLMs, whether it's training on GPUs, whether it's trying to like come up with your own models, right? And so I'm going to take us through all these steps in one simple application we're going to build. So let's do it. Awesome. Yeah. So today we're going to play with this data set called Coco. This was actually from 2017. It's common objects in context. And what this data set gives us is actually a large-scale image data set with object segmentation, in that you take objects or image and you kind of isolate them. So here we see an image with some snowboarders, and we see that this data set actually segmented the different snowboarders and their snowboards from the image. So we're going to play around with it. And now remember, I talked about a data tool that kind of sparks joy. If you're going to write a tool that sparks joy, it's going to be in Python. It's going to have a very simple interface. I want to just do pip install Daft. I want to do import Daft. And when I read from my images from S3 buckets, I just want to do daft.read data format URL. No need to manage other packages. No need to pull in other libraries and dependencies. I just want to do this. So we're going to see, where's this? My credentials. Okay, I'm going to stop sharing and actually log in now. Isn't it that rule that there's no demo that will ever work? So we're back on track. We've logged into AWS. We're zooming back in. We're entering the matrix. And funny enough, when I was building this whole demo, most of my time did go into AWS credentials. So yeah. Okay, so we have Daft.read parquet, S3 URL, boom, we do a metadata read, we know exactly what's in that table. We can do a .show, and very quickly, we see some sample data. I actually forgot I wanted to like log into my own hotspot so that all of us sharing the Wi-Fi won't kind of clobber it. I'm happy that the download speed is actually working really well. Okay, so now we've seen the sample data. We see that there's actually this interesting thing here called the bucket URL, where we are saving the images. It's a common pattern where we actually separate the storage of the parquet files from the image files. So let's go ahead. We need a tool that sees this kind of table, and immediately within the framework itself, we can do a URL download and an image decode, and immediately see what the data contains. So here we see some images from the data set. And I want to pause here for a moment, because if you use any other kind of like data framework, you might think, yeah, this looks great. This is like easy to do in other frameworks too, right? Like if I was using Spark, I can write a user-defined function that will like download images and then decode the images. But remember, this is not a UDF. This is implemented in Rust in our engine. All this is performance code. All this is pipeline. So as you're doing a URL download, as you're downloading your S3 files and reading it as Parquet and decoding the images, all this is happening at the same time. It's not step by step. It's not writing some Python function. This is all happening with performance Rust code at the same time. Now, we said before, we are not just a toy. We have to work with like real-world production workloads. We got to understand catalogs. So let's go ahead and work with Databricks, because this is the catalog I know. So we uploaded the data here to a Unity catalog, and I kind of want to see this Coco images data set, right? The thing that kind of pains me as a shareholder invested uh, member of the Databricks community is that when I try to see sample data, I kind of have to start up a compute to actually view it. So let's go ahead and do that right now. Start a warehouse. I'm going to use my personal compute. This will take 5 minutes. I'm kidding. I'm not going to make you wait. Let's go back. So instead of doing this, let's go back to our notebook and let's view it with Daft instead. We are going to, I already put this in my environment. We're going to like connect to Unity Catalog with Daft. We see what tables are there. Now with Daft, we can do SQL sessions, right? I'm going to create a new SQL session. I'm going to connect our Unity catalog to it. And immediately we can list the tables within our Daft catalog, or within Unity catalog. And now here's the interesting experiment. I want to see how long it takes to get some sample data from this table from Unity catalog. Boom, we got all that data. Let's go back and see how Databricks is doing. I'm gonna go back. It's still starting up. It's still going to take another 4 minutes, so never mind. Let's go back. Let's continue. Maybe at the end of this presentation, we can go back to that. But anyway, now we've connected to a catalog. We've seen the sample data. We did all this in 2 seconds. It's fantastic. Now let's do some SQL, right? Uh, with Daft, all your familiar SQL functionality is there. For example, if I wanted to select columns, all columns on the image table, we can do this in SQL in the exact same performance that we will get in our Python implementation. If you wanted to select specific columns, we can do that. And let's say now, we selected all the columns, we want to like filter the data. Let's say I'm only interested in smaller images with a width of less than 500. We can do this here, familiar SQL, where width is less than 500. You do simple filtering, we can do counts. In fact, we support most of the familiar SQL functions that you would use day to day. We started implementing TPC-DS, which is a common SQL performance benchmark 6 months ago. And I believe we are more than 50% done out of like 100 sample SQL questions in a really short amount of time. Again, these are SQL is not special for Daft. You can mix and match your SQL with your data frame operations. So let's say we did some SQL, we selected some columns, we filtered it, and then we want to do a sort. We can do this very easily. And now you're probably saying, this is cute and all. It's like simple SQL operations. Show me some real SQL. Show me some joins. We can do this as well. So with Cocoa comes with a few tables. Cocoa has Cocoa images, which stores all your image URLs. There's some annotations, which contain like the segmentations and the bounding boxes to isolate the objects from the images. And Cocoa comes with categories saying, okay, you've isolated this thing from your image. This is a person. This is a snowboard. This is so on and so forth. We can do this very quickly with Daft. So we perform a join here. Right now it joins all the 3 tables, and I've only selected these 3 columns from the 3 tables. We support all kinds of joins, all variants, inner, outer, left, right, anti-semi, and that's all of them. Right now we do left joins, which will actually just produce regular inner joins, so you get the same result as before. Let's say you want to do a join, you do some filtering, and then you want to do something more from that. You want to say, do the join, do a filter, and do an image download and decode. We can do this all as SQL as well. So all the operations we did previously with data frames, we can do with SQL. And let's say for the purpose of this demonstration, we're only gonna limit it to 5 rows. Now remember, if we're doing all these expensive operations here, this image decode and URL download is really expensive. We want this to be performant at scale, especially if we are on a local machine and we're kind of like playing around this data set. We want to move quickly. We don't want to spend time, like a minute, just waiting for it to like do joins an entire data set and downloading a bunch of images. So Daft performs uh, pretty sophisticated query optimization. Let's take a look at what's happening. With Daft, you can immediately inspect like what's happening under the hood. If you took the query you had before and you do a .explain on it, you will get the query plan. But this is actually the unoptimized query plan. We can see what Daft will do on a full execution of the query by doing show all equals to true. And remember, this is all like Daft is lazy, right? So when we do this, we're not executing the query itself. When we created the data frame, we're just defining what the data frame was going to do. When we do what .explain, it's just going to plan the query and do an optimization on top of it. And so we do most of the things that you expect. For example, in the original query, we did a filter, we did the image decode and URL download, and then we did a limit. In the optimal plan, we actually push this up, right? So the filter now, from being one of the last steps we do, actually is one of the first steps we do. Because if you can filter out your data early, you can avoid reading a bunch of data and then performing expensive joins and URL downloads on data you don't need. The limit as well gets pushed to happen before the URL download because we don't want to download thousands of images, do an image decode, and then decide that, oh, we only want 5, right? Uh, One last detail to note actually is that if you're doing expensive joins, we do actually reorder the joins. So you see that the join order here, which originally joined a large annotations table, image table, and then a small categories table, this gets reordered to do the least amount of work possible. And so with all this, let's just see how long it takes. Right, so you're working locally, you want to like play around with your data. This takes a second to just like do your transformations and see what's going on under the hood. Now we want multimodal capabilities, right? We take the data, we produce some images. What can we do with it? Let's crop it to the bounding box. So recall that previously we saw all these images that annotated as person, but for some of them we can't really see a person inside it. So if we crop it to the bounding box, we actually see that, oh, the person pops up, right? Because these are images, it's like we're taking a segment of the image and then you see the person is only a very small part of the image. We can say, okay, we want to start doing some model training or like make some LLM calls with this. Let's normalize all data, resize it to a standard square. We resized it, and let's say I want to, yeah, so now they're all squares. Let's say I want to exclude columns I don't care about. I just want the original image ID, the annotation ID, and the resized image. And then let's say I want to encode all these things back into JPEG. So all these happen, and we've transformed the data, and now we're ready to maybe do some more work on it. Now, recall at the very start, we kind of like limited this to just 5 rows of data. Now I want us to actually scale this up. We're going to do like a full data engineering pipeline over all 45 gigabytes of data. And we're going to do this very quickly just by jumping to the AnyScale platform. So we left off here. This was the last cell we were on the local side. But anyway, when we talk about local to seamless local to distributed development, there shouldn't be like this jarring change where like you suddenly need to think a lot about your distributed architecture or what's actually happening under the hood with all your machines talking to each other. You should just do the same thing you're doing locally and just run it on a cluster. So with Daft, how does this look like? In Daft, it's just this line. We're gonna set context. We're gonna take the context and set the runner to Ray. That's all. That's all you need to do to use Daft on any scale. We do some additional like planning configurations here. This is to work with AWS credentials, right? That was where most of my time preparing for this talk went into. Um, so now that we're here, I'm gonna do this thing. I prepared a larger data set with 45 gigabytes of images. We're just gonna take a look at what's in this data set. So now, we're on Ray, we're auto scaling. There were zero workers at first. Now we have 1 node. It's launched. It's gonna take a second to run. I'm actually also gonna go ahead later and scale up even more. I guess here we can see what's actually going on. So one active node now. We got one. It's running now. It's not idle. Ah, okay. It's up and running. Great. So we got an image. The next ones are gonna happen faster. So we have that node up and running. We can see we have the three tables we had at the start. We had the image table, the annotations table, and the categories table. Now we're gonna do a join on these three tables. And I'm gonna do a dot collect actually. We're gonna like join everything and then cache the results in memory. So now we see we're actually increasing the cluster size from 1 to 20 nodes, launching all of them, running a scan, doing a broadcast join. We can see all of it going. It's all going now. I don't know. I think it's pretty cool to look at the metrics and just see uh, what's actually happening with your cluster. But great. So we're doing a large scale join now on the full Coco training data set. Yeah, look at that. Look at the utilization go up. 16, 17, two more pending, 18. Beautiful. 160 CPUs. It's almost there. Yeah. I don't know if anyone's timing this, but like it's been about a minute, I guess. We've basically like combined all the Coco training set. So it's actually pretty good. Um, guess it's just doing the final project now. Yeah, okay. We've completed everything. Great. Uh, now to really see things zoom, I want to just do a little experiment here. We're gonna see what happens. We're gonna take all tables that we join together. We're gonna do a URL download, and then we're gonna download all the images, which, um, we're gonna see how much data there actually is in there, and then we're gonna sum up the length or the size of all the data we downloaded, and let's time it to see how long this whole operation takes. Okay, so we do a URL download. It's all lazy, it hasn't executed yet. I'm gonna run this aggregation now. I don't know if anyone's seeing it, but up here, our CPU utilization jumped all the way from 0 to 160 in the time it took. Is it done already? It's done. Great. Yeah, it jumped all the way up, it jumped all the way down. We downloaded the whole 45 gigabytes of data in 7 seconds. I don't know, I think that's amazing. So let's do that. We can go ahead, we do the pre-processing we wanted, and then we can write it out to our S3 bucket. I'm not gonna wait for that to happen. I did pre-populate it. Um, yeah, it's going. But anyway, let's continue. Now we've seen how we work with Daft to like explore with our data set. We figure out what kind of transformations we want to do with our ETL pipeline. We did all that in Ray. Uh, I know we sat around waiting for a minute, but in a minute we got to like the whole pipeline running and completing. So that was pretty cool. And now let's see what we can do with this, right? So Daft, when I say data and AI, we kind of like one or two where you can go back and forth a lot. We explored the data locally, we scaled it up. Now when we do AI application development, we can do it locally too. So I'm going to go ahead and read from that bucket. That's my credentials again. And I think we are back in action. So I went ahead and ran it. What this does is it's going to read back from this bucket we just wrote into, and that we're actually still populating on the array side. We're going to take a look at what images we put in there. So there's some people in here. We crop them and we resize them. Now, what we're going to do is we're going to write a user-defined function that's going to make an API call to OpenAI. And we're going to say, hey, please score this image on how formally the people in here are dressed. Please score how confident you are in your assessment and give me a reason for why you gave me those responses. We're going to go further and we're going to use instructor to make sure that OpenAI conforms to this specific schema we provide, right? So we're going to do that. And we're going to provide a pydantic model to ensure that everything is going to come out as two floats, right? The score of the formality, the score of how confident it is, and the score followed by one string, which is its reasoning. So we're going to go ahead and do that. We're going to make a call as a UDF to the data frame. So we're just going to take the data frame I had. I'm going to create a new column called response, and we're going to call this user-defined function on it. It's all lazy. It didn't happen in just an instant. OpenAI is not that fast. And yeah, and I'm gonna just clean up the output since we have all this extra data there. Cool. Now we're actually gonna run this, and we're gonna wait to get back some results. It's making calls to OpenAI right now. It's probably gonna take a second. Yep, this is the part where it's making the API calls. Boom. Okay. So we made a bunch of calls to OpenAI, and what we see is that it's given a pretty harsh ranking, almost everyone's dress attire, where everyone gets a very low formality score. And except this fella wearing a suit got a 0.8 out of 1. Nice, good for him. Uh, yeah, but of course, there's a lot of this data set has a bunch of like blurry images or dark images or obfuscated images. And here we see OpenAI is like not confident in its assessments of some of these because there's just not enough information. So let's say you're curating your data set, right? You process it with OpenAI. Let's say we just want images where we're confident in the score. We do that, boom, immediately we get all the images from this specific run. We get the scores and only scores for images that we're confident in. That's it, we've done it. So that's the end. I just want to remind people where we came from, right? We came from this fella being disappointed in all these AI tools and writing an AI application, and the most painful part was AWS credentials. I think that's a great journey. And now I'm gonna pass the time on to Ricardo to talk about the last two parts here, more about AnyScale, and I imagine more about ray train or some other things. So yeah, I'll pass it over. Thank you, everyone.
Uh, I want to give another round of applause to Desmond for being so brave to do a live demo. It's always nerve-wracking. So yeah, good job. All right, cool. So my name is Ricardo. I'm a PM at Anyscale, and I'm going to be talking to you today about how Ray Train allows you to efficiently scale training workloads on, scaling training workloads. So some quick background, quick trends on AI, if you haven't been paying attention. We're getting bigger, 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 right? So bigger models, more data, and including different modalities, more training time, and new specialized hardware to support these new AI workloads. And the as you get bigger in scale, it forces you to distribute your workloads across many machines. Okay, you can't just run these on a single machine. So if distributed workloads are here to, it's a new norm. Um, you need to be aware of the different challenges that brings along. So these challenges include setting up your distributed environment, right? When you have all these different machines, you have to set up the software on them, make sure that their environment variables are all networked together and things like that, making sure that your workflow works across many different machines, being able to debug a system that's spread across many machines gets really complicated. Being able to handle hardware failures as you add more and more hardware, uh, uh, things start to happen. GPUs blow up in a data center or something. You need to be able to handle that. And finally, the data complexity is grows with that. So today I'm going to be talking about Ray Train and how it takes care of all those problems. So Ray Train is the best way to take uh, machine learning code that runs on a single machine and spreading it across many machines. So at the top layer, you have your application layer, you have PySpark, XGBoost, all of these frameworks that you're familiar with. Ray Train kind of is a thin wrapper around that then uses Ray Core beneath it to do the cluster management and run it across many machines. So that could be on-prem, that could be on Kubernetes, that could be on AWS, whatever cloud that you're running on. So yeah, that's the talk in a nutshell. A little bit more on Ray. Ray is this AI compute engine. It's like a general substrate for scaling up compute on clusters. So the cool thing about it is that you could take your Python code, do minimal changes to it, and then all of a sudden it becomes distributed code, which is pretty slick. And because of this, there's this growing ecosystem around Ray. So like Daft is built on top of Ray, also VLLM, CubeRay, RayTrain, which this talk is about, is built on top of Ray, etc. So that's it about Ray. Going back to RayTrain, we're going to talk about the first challenge, which is setting up a distributed environment. So it's pretty simple. If you just encapsulate your training code into a function, you set up a scaling config, which is our abstraction for how you define what a cluster looks like. So in this example, you're looking at 4 GPU nodes, but you can do a bunch of different examples. So over here, we have a CPU-only cluster. We have a cluster full of A100s or TPUs, whatever, right? There's many ways that you could define a cluster, right? Then you just package these together, right? You have your training logic, you have your scaling config, you put it into this thing called a trainer class. In this example, since we're using Torch, it's a Torch trainer. And then you do trainer.fit, and literally that's it. So if there's one key message in my whole talk is that RayTrain allows you to quickly turn code that runs on, like, let's say a laptop or a single machine and distribute it across a cluster. Okay. So what happens when you do this train.fit? First of all, Ray starts setting up your cluster, right? In this case, we have a scaling config with 4 workers, 4 GPU workers. So it launches those. Okay. It sets up the environment on those workers. So it'll set up the code, sorry, the requirements on them, the environment variables, network them together so that they're aware of the cluster topology, right? And then it starts executing your training function. So this is your actual code that is training things. In this case, since it's PyTorch code, PyTorch is actually what's training your model, and Ray kind of gets out of the way, right? So it sets up all the plumbing and then gets out of the way, and PyTorch does your actual machine learning training. Cool. So the next thing I'll talk about is how you could use your machine learning workload on a cluster. And basically, we do this through integrations. So we work with PyTorch, with TensorFlow, with XGBoost, whatever code that you're working with, whatever experiment tracking. We have all these lightweight integrations with WanDB and et cetera. And also, Ray makes it possible to have portable workloads, right? You're not locked into GCP or AWS. You could take things on-prem, wherever you may need without having to like rewrite all your code. Next, I'm going to talk about debugging. So for anyone that has spent significant time with distributed systems, they probably have a lot of pain with debugging. So you go from one machine where it's very easy, right? You have your profilers, you have your logs, et cetera. And all of a sudden you go distributed and, some worker is failing for whatever reason and you don't know why, right? So we have this dashboard, Ray dashboard, which in the interest of time, I'm going to kind of gloss over slides, but basically it lets you do monitoring, seeing like what cluster usage is going on. You could read the logs across the whole cluster. That's kind of a big deal. Metrics, profiling, et cetera. And so this is just like a general view for any Ray workload, but we also have a Ray train specific dashboard, which for each one of those things that I just mentioned, they have particular things for Ray train, like the training throughput, et cetera. And if you have, like, let's say a worker hang, um, ordinarily this would be kind of complicated, right? You would have to kill your training script, add debugging statements, run it again, start SSHing into the individual nodes, doing profiling, et cetera. With ray train, it's easy peasy. You could just click in and see what's going on. Great. Next thing is handling hardware failures. So I use hardware failure in a very kind of hand wavy way. It could literally be like a GPU blows up uh, in a data center, which is a thing that has happened to me more than once. And you could lose a whole training run, or it could be as simple as like a networking hiccup where a cluster becomes unreachable, or it could be that your instance gets preempted. So for those of you that don't know, there's these things called spot instances, which is where there's spare capacity in, let's say, AWS. So they give you a deep discount, like 90% discount. However, the catch is that they could yank away the machine from you at any minute, right? So if you have fault tolerance and a highly interruptible workload, you could save a lot of money using spot instances. So the way that this looks like is basically if you have a GPU node and it gets killed, let's say it blows up in a data center, um, the cluster goes into recovering mode and kind of pauses while the GPU gets requested and gets set up. And once the node is added, then training gets resumed. Okay. So that's really nice. And doing this is very easy. It's just a few lines of code. I'm just kind of skipping ahead in the interest of time. So elastic training is when you could have a dynamic cluster size, and ray train lets you do this pretty easily. So what that looks like is when, let's say, a instance dies or your spot instances go away, you can elastically scale your cluster and training never gets interrupted. It just keeps on happening the whole time until the cluster scales back up. So yeah, doing this is very easy. Just in the scaling config, you could give it a range and it works. Cool. The last thing I'll talk about is large data complexity. Yeah, basically, these data loaders look kind of familiar to Daft. This is with Ray Data. Now it's a separate library within the Ray ecosystem, and it's a Pythonic interface for mapping batches, and it'll be very familiar if you're from the PySpark world. Now, one nice thing about uh, running things on Ray Data is that you could independently scale your data processing from your training. So over here on the left side, we have a bunch of machines that are running your data preprocessing that can automatically scale elastically separate from your ray train GPU nodes. So that's very nice. If you get more GPU nodes, all of a sudden the CPU nodes can react and elastically scale to saturate those GPUs. Okay. And yeah, you could have heterogeneous clusters, some CPU nodes, GPU nodes, different types of GPU nodes, et cetera. Over here, Desmond kind of talked about this, how you can have lazy execution, streaming execution. So the nice thing about that is you could have a very, very large training data set, hundreds of terabytes, and you don't have to load it all up into memory. You could, on the fly, be streaming the execution through. So that's a must-have for very large scale. Um, Basically, differences between array and data, Ray data and Daft is mainly the API, right? So Daft is a very pandas data frame sort of API. Ray data is more of a like chainable functional style. Daft has better SQL support than Ray. So if you're trying to like port over your PySpark workloads and you have a lot of SQL statements, Daft might be better for that. maybe rate data might have an edge with unstructured workloads, but there's good interoperability between them. So, choose your poison, whatever style you prefer. So yeah, I wanted to illustrate all of this with a case study on stable diffusion. I'm going to gloss over a lot of the details, but basically each training sample is a pair. You have an image and a caption. Each of those get encoded separately. You get these two embeddings. You pass them through a UNet model. You get a loss and you minimize a loss. Okay. So this comes with its own challenges. The main one is the scale of the data. We're talking about hundreds of terabytes, billions of images. That comes with its own set of landmines where you might like get objects spilling, and it's kind of a mess, right? It's also a very long job, right? 13,100 hours. So you want fault tolerance, you want interruptibility and being able to resume, and you want to really saturate your GPUs. If you're spending tens of thousands of dollars training this thing, you don't want to, have poor GPU utility. And yeah, like the pre-processing is more complicated than a typical machine learning use case. So a kind of simple way of doing this is just having every machine do all the different parts all at once. So here we have a whole pipeline on every machine. The problem with that is when you look at uh, the log, so over here on the x-axis is time, on the y-axis is the GPU memory, which is, you could think of as a proxy of the GPU utility. GPU utility is most of the time very low. And you're spending a lot of time on the encoder's forward stage and only using like 25% of the utility for 30% of the time. Not great. So basically, this half of the pipeline is the bottleneck, okay? So that's kind of wasteful. So what if we decoupled it? So one way of doing this is to basically pre-compute all of the embeddings and put them into S3. So basically over here, you get all the images and text, you put them through these encoders, dump them in S3, and then later on train with them. So this offline pre-processing is nice because you could do it on cheaper machines that are interruptible, it doesn't matter. And then you can train with a more expensive machine later, okay? And this gives you a nice little speed up over just doing it with PyTorch data loaders, okay? But what if you wanted to do dynamic pre-processing, right? So instead of having the same image all the time, you want to crop it, you want to do data augmentations and on the fly just kind of randomize things. Well, you want to maintain this sort of decoupled architecture, but instead of dumping everything into S3, you could do it all end to end, right? So instead of having an offline step and an online step, it's all end to end online, except over here, you're keeping the intermediary data in the kind of pooled cluster RAM. And crucially, since you have these two decoupled steps, you can scale these cheap nodes until you saturate the more expensive A100 nodes. Okay. We keep the same speed up as before because the A100 nodes are saturated. You're not getting any more gains. So it's nice that you could get this equivalency. But this blog post talks about all these different optimizations that we do to get like a 300x, or sorry, a 3x performance boost by speeding up the UNet stop. So yeah, in summary, ray train, when you are distributing your code, you get a bunch of complexity, a lot of pain, but ray train kind of abstracts away all that complexity and pain. So yeah, that's our talk. We are hiring. So if you're interested in these sorts of topics, please reach out. Cool. Thanks.